Good evening. Today we will be discussing about the FIR filter, digital filter designing using the Fourier series method with windowing technique. In our last class, we have been discussing it about the Fourier series method without windowing technique. Okay. So, what is the goal of this method? The goal of this method is to create a practical finite length filter that approximates a desired or ideal frequency response. Okay, an ideal filter, example one with a perfectly sharp cutoff, has an impulse response that is infinitely long, making it impossible to implement. And lastly, the windowing method resolves this by truncating the ideal impulse response to a final length. Okay, in our last class, what we were doing, we are just selecting the values. So because of that, and those values were from the ideal response. Okay, so because of that, what was happening? Suddenly we were having one, and suddenly after a cutoff frequency, it came down to zero. Okay, so when we try to implement this kind of things, we have seen that we may have or we may face this Gibbs phenomena effect. Okay, where there will be ripples over there. Now these ripples, they are not good because these ripples, what it does, it is deviating from our idealness. Okay, and it induces some noises into the signal itself. So, to avoid that condition, we have this windowing technique method. Okay. So, initially, if you look into the steps will be similar. So, if you see, first draw the frequency response. In our last class, we have seen we need to draw the frequency response. Then we needed to calculate the impulse response Hn. Then, after calculating the Hn, we were directly going to the calculation of the Z transform, and from there realization we are going. However, here we are having two extra steps. What is this extra step? The extra step is the first one, calculate the window coefficients Wn, and the fourth one is calculate h dash n. What is h dash n? We calculated hn values multiplied by wn values that will be calculating in the step 3. So that would be our h dash n. Okay, so hdn, it is basically this hn, because this is this hn is for the desired frequency response. Hence, this hn is also regarded as hdn. Okay, h desired n, hn with the desired frequency response multiplied by wn, which are the basically the window coefficients. Okay, so we calculate this h dash n. Now once we calculate this, then the step remains the same. For this, using this h dash n values, we will be performing the or computing the z transform, and lastly we will be realizing that filter. Okay, so purpose of windowing. So as we saw with the Fourier series method, simply cutting off the ideal but infinite response is equivalent to using a rectangular window. This abrupt truncation causes significant ripples in the passband and the stopband of the final filter. Okay, so that we have already discussed. Okay, now when we use the specialized window, which are regarded as the window functions, it helps in the smoothing this truncation. Okay, so instead of an abrupt cutoff, we will be getting a windows, smoother windows that taper the impulse response coefficient. So ideally, what we are having. So suppose this is the ideal this thing. The coefficients were something like this, and then suddenly it was becoming zero. Now what will happen when we use the filters? So we may have something like this. Okay, so there is a gradual decrease in the amplitude response. Okay, so how the window works, as I told you, Hn it would be equals to hdn multiplied by wn. Okay, so this is the important thing. So what are the common window functions? The common window functions are the rectangular window, which is similar to the without window method, because here in the rectangular window we will be having values either 1 and 0, but for the sake of making you understand how the computation persists, so first example we will be taking it with the rectangular window, and then we will be taking another window, and I will be giving you the equations for all other windows. So you just need to go through those equations, you have to memorize that, and if you get an this question numerical on that part, then you have to implement it just by putting the values of n, small n. Okay, so rectangular window, so this is no window case of abrupt truncation, so it provides the narrowest possible transition band. Transition band is, see, there is a gradual decrease, so if you calculate the cutoff, suppose this is the cutoff a by root 2, okay, and then this is the stop band. So this frequency, from where the stop band start, this cutoff frequency starts, and before the starting of the stop band, this band it is called the transition band. Okay, it is also regarded as the roll off region. It is also regarded as the roll off region. Okay, so apart from the rectangular window, we have Bartlett or triangular window. We also have the Hamming window, and Blackman window. Okay, so under usual circumstances, you will find that for biomedical applications, we use either Hanning window or Hamming window. Okay, so these are the equations. So here the equation is for the rectangular window. If you see Wn equals to 1, for Bartlett or the triangular window, it is Wn equals to 1 minus 2 of modulus of small n minus capital N by 2. This same is basically our this order of the filter capital N. Okay. So then we have the Hamming window, then we have the Hamming window, and then we have the Blackman window. Okay. So what we need, you need the order of the filter, and n values, it will be coming from 0 to capital N. Right? It will be varying from 0 to capital N. Right? So this is the architecture of the rectangular window. Bartlett window, triangular window, it looks something like this. Then your Hamming window, it looks like this. Okay. Hamming window, if you see, the coefficients are slightly raised, so it is also sometimes regarded as the raised Hamming window. Okay, raised Hamming window. If you see this over here, the coefficients at the extremities, it is coming out to be 0. But in the case of Hamming window, this is raised slightly. It will be having some slight increased value. Hence, this Hamming window is sometimes also regarded as the, oh, sorry, no, this is the Blackman. Sorry, this is the Blackman. No, yeah, Hamming is this one. So, so if you see here, it is again, it is the 0. But when you look into the Hamming, so its values are slightly raised, and hence it is called the raised Hamming window. Okay, and then we have this Blackman window. Again, if you see, we are having this thing. However, the skewness in Blackman window, it's slightly greater than the Hamming or the Hamming window. Okay. So over here, there are two components. So the first component is the transition band. Okay. So which results in the sharp cutoff. In narrow transition band, it will lead to the sharp cutoff, and a high stop band, it will lead to low high stop band attenuation. It will lead to low ripples. So these are the two trade-off points, and we need to work with these two points. So if you need a high cutoff, so if it is a sharp cutoff, your ripples will be quite high. Okay. If you are having sharp cutoff, ripples will be high. And if you want a low ripple system, then your transition band or the cutoff should be gradual. Okay, should be gradual. So we cannot achieve sharp cutoff and low ripples at once. So somewhere we have to come to a trade-off point. Okay, and this is what it has been written over here. So the main trade-off happens between the transition width or the transition band and the stop band. So these are some of the these window types. So rectangular window, if you see, for the rectangular window, it is being shown by red one. So it is having a sharp cutoff. Okay, if you see the transition band, if you consider minus of 3 dB as this thing. So if you see, this is having very sharp cutoff. Okay, then Bartlett or triangular window, wider than a rectangular. So Bartlett grain, see, it is slowly, gradually coming down and it is then standing out. However, if you see the side lobe attenuation, it is only minus 26 dB. Now, if you consider this Hamming and Hanning window, the main lobe, it is wider than triangular, okay, in both the cases. However, if you see the side lobe attenuation, it is minus 42 dB, and in Hanning it is minus 31 dB, which is far far better than the triangular window. Okay, and also if you look this thing, this Hanning is this dark fluorescent blue, and Hamming is this cyan this thing. So you can see it is quite lower. The Blackman, it is also quite low. It is having minus 58 dB, and if you can see, it is the more gradual. It is more gradually coming. So now, I think you should be able to appreciate what is the difference between the transition and the ripples or the attenuation. Okay, so transition in the Blackman, it is happening more gradually, and its ripple are quite low. And on the other hand, in the rectangular one, it is having a very sharp transitions, but its ripples are very high. Okay. However, if you look into the Blackman equation, it is computationally more complex as compared to the Hanning and Hamming. Okay. So for biomedical application, due to this reason, because the Hanning and the Hamming window, they are having a bit lower computational complexity. So these two windows, they are very commonly used. Now, benefits of using the windows in FIR filter. So the spectral leakage, that means this spreading of the frequency components into adjacent frequency component, it reduces. So we can have control over the side lobe levels because our ripples, they are subsiding. Then since there is a reduction in the spectral leakage, there is an improved frequency resolution. Okay, smoother transitions are happening. Design flexibility, we can have a large number of window functions. From there we can choose which window function we need to use. Okay, so less ripple in the passband and the stop band. Okay, simplified filter design and enhanced performance. So let's talk with the example. Let's take up the example. Design a low pass filter using rectangular window by taking 9 samples. 9 samples means order will be 8. Samples mean length. Samples mean length. So our length is L, which is equal to 9. So our order N or capital N, if you take the example of the equation, it is equal to 9 minus 1, 8. So order would be 8. Now if you see over here, I have slightly changed the equation. Okay, I have slightly changed the equation. So what has happened now? Ht omega, it is equal to e to the power minus j omega alpha. Okay, e to the power j omega alpha. Now what is alpha? Alpha is equal to L minus 1 divided by 2. Okay, which is equal to, in this case, it is 4. Okay, So what has happened? Rest of the equation, if you see, it remains the same, and the method remains the same. But what has happened is that now if you see, we start with n equals to 0, and at alpha position, alpha equals to n, which is equals to 4, we'll be getting this condition where we need to apply the L'Hospital's rule. So what we have basically done, we have simply shifted the negative time coefficients into the positive time coefficients, and we have made the system causal in nature. Okay, we have made the system causal in nature. Okay, we can implement the same thing in the previous example also, but that was the conventional method of designing. But slowly when this window system came, so people, a window, it is being designed in the 0 to n levels, capital N, what you call, n band. So what happened is that there was a slight tweaking of the equation just to shift the negative time domain coefficients to the positive time domain coefficients. Okay. So once you have done this, you have calculated all these Hn values. Just then you calculate the Wn values. So it is given W0 equals to W1 equals to up to W8, it is equal to 1. Okay. Then what happens? H dash n equals to hdn multiplied by wn. So what happens? How do you calculate? H of 0 minus of 0.08 multiplied by w0. Okay. Then h of 1 multiplied by w of 1. Then h of 2 multiplied by w of 2, in this fashion. Now how you will be implementing the Z transform. Now our band is n band is 0 to capital N. So you just have to apply, take the values and just put z to the power that n value. In the previous case, we had to, in the z transform equation, we needed to include this z to the power 5 multiplied by some fraction was there, so that we could convert the negative time domain to the positive time domain. Okay. However, just by simply tweaking this equation, we are able to get all the coefficients in the positive time domain. Okay. So once you have calculated the exit, you can then go for this what you call realization of the filter. Okay. Then similarly, design a band pass filter uh, having pass frequencies in the range of 1 to 2 radians per second using Hanning window with length equals to 5. If length equals to 5, order is equal to 4. HDN, HD omega equals to e to the power minus j omega alpha in the region of omega c less than equal to modulus of c1 less than equal to modulus of no, omega less than equal to omega c2. That means in the region of omega c1 to omega c2, we will be having these values. So we will be, since it is a band pass filter, we will be having these two integrals. We need to solve this. So after solving this equation, we will be getting this equation, and then we will be having this h dash n value we need to compute. So h dash n is equal to hdn multiplied by wn. So what is the wn equation? Wn equation is this one, 0.5 minus of 0.5 cos of 2 pi n divided by L minus 1, or this order of the filter capital N. Okay. So calculate these wn values, and you are having this hn values multiplied by this thing, this compute, and once you have got this, you go for the computation of the edge set. Okay. So for Hamming window and Blackman window, also we can go in this fashion. So next is the FIR sampling, yeah, frequency sampling method that we will be covering up in the next class. So you please, um, this is the rectangular window, so there is no need to do this. You please solve this one and try to find out whether you have got hold of this or not. Okay, so 1 to 2 radians. So this one is uh, omega c1, omega c2. Okay, so minus of omega c1, omega c2. So we'll be going from here to there. So minus of omega c2 to omega c1, then omega c1 to omega c2. Are you getting my point? So minus of omega ct to minus of omega c1, and then the next integral is omega c1 to omega c2. Okay, so do this. Now suppose I give you, say, instead of band pass filter, if I give you, to design the band reject filter, then what will happen? So it is minus pi to pi. So here it should be minus pi. In the band reject filter, this should be 0. So my frequency response would be something like this. Then something like this, and then something like this. So what we will be having, this is the direction of integration. So minus pi to minus of omega c2 plus minus of omega c1 to omega c1, नहीं नहीं यहाँ से है ना, माइनस ऑफ ओमेगा c1 टू ओमेगा c1 प्लस omega c2 to pi. Okay, so it is always better to look into this thing, because in this band reject filter we will be working in this region. Okay, so always it is always better to draw this impulse response figure and then calculate your. It will take some time, but it will be easier for you to determine the limits.